This is the Old Bailey. Today, it's the Central Criminal Court. But until the mid-19th century, this site was home to Newgate Jail, the most notorious prison in Britain. On the morning of the 18th of January 1803, George Foster was taken from his cell here in Newgate Jail and led down this corridor. The reason this corridor narrows as you walk down it is that as prisoners were led down here, they had a tendency to panic. And that's because this is the last walk they made of their life. And this was the route to public hanging. Vast crowds had gathered outside the jail to witness George Foster's last moments. According to one contemporary account, Foster died very easily as several of his friends who were under the scaffold had violently pulled his legs in order to put a more speedy termination to his sufferings. Now, Foster's hanging was an unremarkable event. Public executions were common in 19th century London, but what was unique was what happened to Foster's body after he died, because it was taken directly from the gallows to an operating theatre. George Foster's corpse was to be the centrepiece of a public demonstration by Professor Giovanni Aldini, a practitioner of the latest field of scientific experimentation. Galvanism. Galvanism was the belief that electricity was the spark of life, perhaps even the very essence of life itself. And this is what Aldini intended to demonstrate by taking a pair of electrodes and in front of the watching audience, thrusting them into George Foster's corpse. To the audience's amazement, the dead body in front of them twisted and contorted. When current was applied to the face, the dead man opened his eye. Aldini was hoping that through these experiments, he would one day be able to bring people back from the dead. For many watching in the audience, this was a step too far. It was outrageous, immoral even. And ultimately, Aldini was forced to leave the country. A few years later, Mary Shelley wrote her seminal work, Frankenstein, the story of a corpse brought back to life. And it's said that the eponymous scientist was based on Aldini himself. This image of scientists as Frankensteins, meddling with powers beyond their control, is a vivid one that colours the public's perception of science to this day. The idea of mad scientists creating dangerous monsters has haunted the story of British science. In this film, I want to find out why. I'm going to visit the locations where some of the most controversial discoveries in British science were made, and examine the impact they had on the world.
It provided a physical explanation of heredity.
I'll be looking at scientists whose research horrified the public, and I'll be meeting researchers whose work remains controversial to this day.
I never had any doubts about the benefits that accrued from the work that I was privileged to be involved in. I'm not embarrassed about what I do.
Science is one of this country's great success stories. We punch way above our weight. I mean, just look at this view. Over there, In Paddington lived Alexander Fleming, whose discovery of penicillin transformed our treatment of bacterial infections. There, on the other side of Regent's Park, lived Michael Faraday, whose work in electricity and magnetism, electromagnetic induction, made electricity a practical and useful thing. And there, on Gower Street, lived Charles Darwin, where he first formulated his theory of evolution by natural selection, which transformed our view of the natural world. It's these discoveries that shaped modern life. And this from just one tiny slice of the country. Across the whole of Britain, our contribution to global science has been enormous. But while Britain has been the location for so many of science's important discoveries, it's also been a place where discovery can be controversial. A place where science and scientists can still be treated with suspicion. And to find the reasons for that, we have to go back in time to when science had caught the public imagination as never before. In the early 19th century, Regency London was at the centre of an intellectual revolution. It was a place of great art and great architecture. And the rock stars of the time were the romantic poets, mad, bad, and dangerous to know. But equally famous and arguably more dangerous were the natural philosophers, or as we call them, the scientists. At the time, science was transforming the way we understood the world, and the public were desperate to hear of the latest advances. Lectures given by the top scientists of the day would be sold out. And in 1802, the hottest ticket in town was the Royal Institution, where the star attraction was their new Professor of Chemistry, Humphrey Davy. Humphrey Davy was a Cornishman and a brilliant scientist. He became professor here at the Royal Institution at the unlikely age of 23. He was good-looking, charismatic, and many said arrogant. He thought he was a genius, and he was probably right. As well as being a brilliant chemist, Davy was also a passionate communicator of science. Davy was a genuine star. The Royal Institution Theatre was packed with the great and the good of the day. They had come to witness Davy's spectacular demonstrations. It had all the excitement of a magic show, but what Davy was doing was better than magic. It was chemistry. Davy first carried out this experiment in Italy, and what he was interested in doing was setting fire to diamonds. Now, hang on a second. They're very hard to hold in the tweezers. When it is white hot as I can get it, then I'm going to drop it into liquid oxygen, and what should happen is the diamond should catch fire. As the diamond burns, a single product is produced, the gas, carbon dioxide. Through this experiment, Davy was able to deduce that diamonds are made solely of carbon, that the most valuable gems were made of the same stuff as coal. To Davy's audience, this was captivating. Here, in front of their eyes, he was demonstrating one of the latest scientific theories. That everything is made up of a limited number of elements. Davy was famous for doing spectacular experiments, in particular for blowing things up. In fact, it said that he was something of a pyromaniac. And this is one of the experiments. It's involving iodine, which is in fact one of the elements Davy is famous for discovering. So, Davy mixed iodine with this liquid, and what happens is a powerful contact explosive is made. And in one of his experiments, he temporarily blinded himself by doing just what I'm doing now. Now, what Davy wanted to do was to educate his audience. He wanted to show them that chemistry was exciting and counterintuitive. This idea that you can make compounds out of other substances that have extremely surprising and, in this case, spectacular properties. Nitrogen triiodide is a wonderful compound for demonstrating those ideas. It's basically a nitrogen atom with 3 iodines stuck to it. Now, nitrogen atoms want to interact. They want to bond together into the very stable nitrogen molecule, but the iodines keep them just far enough apart that they can't interact. All you have to do to change that and make them interact very quickly indeed is to give them a little tickle. And it really is a very little tickle. Look at that. And that purple vapour there is iodine. So that was a very rapid chemical reaction. Nitrogen is produced and iodine is released. I see why Davy liked that. What Davy was demonstrating is that acquiring and applying scientific knowledge gives us power over nature. And his writings reveal how he believed our future lies in exploiting this power. Science has bestowed upon him powers which may be almost called creative, which have enabled him to modify and change the beings surrounding him, and by his experiments to interrogate nature with power, not simply as a scholar, passive and seeking only to understand her operations, but rather as a master, active with his own instruments. Here, Davy is echoing the language of the Romantic poets. When he uses the word creative, he doesn't mean the qualities required to write a novel. He's talking about being a creator in the biblical sense. Of controlling nature. Davy is claiming for science the territory previously occupied exclusively by religion. And not everyone was so enamoured with the idea of scientists playing God. Shortly after Davy wrote those words, Mary Shelley wrote her famous Gothic novel Frankenstein. And here in the introduction to the 2nd edition, she writes, "For supremely frightful would be the effect of any human endeavour to mock the stupendous mechanism of the creator of the world." I mean, here is science with the dark side. Frankenstein becomes a stereotype, a view of science as darkness as well as light. Scientists can also create monsters. At the time, Mary Shelley's fears were not widely shared. The majority of the public remained in love with science for another century. Just as Davy had predicted, we discovered more and more about how the world works and learned to control it. But as our scientific understanding increased, so too did the potential for that knowledge to reveal a dark side and unleash monsters. "70 years ago, this nature reserve in North Wales was the site of a top-secret military facility, at the heart of both the war effort and British science. This was the home of a chemical warfare project. It's where mustard gas was manufactured.
We are ourselves firmly resolved not to use this odious weapon unless it is used first by the Germans. Knowing our hunt, however, we have not neglected to make preparations on a formidable scale."
But the site housed another, more exciting, more dangerous project. Eileen Doxford was one of the handful of people who staffed it. In 1942, Eileen was just 19 when she was assigned to work as an instrument technician on a project codenamed Tube Alloys. So this was the main building?
Yes, it was. It was. Lots of apparatus in it.
And how many people worked here?
Well, there were 70 men and 10 girls.
You met your husband here?
I did. If I couldn't have found one out of those, I would have been not much good, would I? At one side of this building were offices and a laboratory.
Did you know about the importance of the work you were doing here at the time?
Well, to be really honest with you, I didn't understand what we were trying to do here. I quite happily did the job that I'd been given to do, but I didn't know. Oh, no, I didn't know. I was told that it would be helpful during the war, and it would also be helpful in peacetime, but it would be particularly of help in wartime.
Eileen didn't know it, but she was working on the project to create the most powerful weapon the world had ever seen. The origins of this weapon lay not in military research, but in scientists' ongoing efforts to understand the structure of the world, and from some brilliant experiments performed 30 years earlier. The nuclear project began with this man, Ernest Rutherford, who worked at the greatest university in the history of civilization, the University of Manchester, which is my university. Back in 1911, only 28 years before the outbreak of the Second World War, there was no nuclear physics because we hadn't discovered the atomic nucleus. That's what Rutherford did. In a series of experiments, he found that the atom itself is made up of a small, dense nucleus with electrons existing or orbiting in some sense a large distance away. But at that time, the nature of the atomic nucleus was completely mysterious. So Rutherford, one of the world's greatest experimental physicists, set about designing the apparatus that revealed the structure of the atomic nucleus. With little more than some dry ice, a hot water bottle, a squirt of alcohol and a radioactive source, he was able to visualize with the naked eye things that the most powerful microscopes struggle to detect. Individual subatomic particles. Well, this is the cloud chamber full of supersaturated alcohol vapor, and you see those cloud trails? Those are helium nuclei, alpha particles, single ones being emitted off the thorium on the end of that welding rod. It was these particle trails that Rutherford watched, hoping to see what happened when atomic nuclei collided. Now, very occasionally, very rarely, they saw something extremely interesting happen. And we have a graphic of that here. So now this is a picture, a film of a real cloud chamber, and we've superimposed there a graphic of what Rutherford and his team saw. The reason we haven't shown a real one is because these are extremely rare processes. Rutherford observed over 250,000 tracks of helium nuclei passing through the nitrogen, and his team only saw 8 of these particular collisions. Now, at first sight, it looks unremarkable. There's a helium nucleus coming in, bouncing off a nitrogen nucleus. The interesting thing is what these two outgoing tracks actually are, because they are no longer helium and nitrogen. This one, it turns out, is oxygen. And this one is a single proton, the nucleus of hydrogen. This is an extremely important moment in the history of nuclear physics. It says that nuclei are not indivisible. Elements can be transformed from one type into another. It was known that when some nuclei are split, energy is released. But no one thought it would be possible to harness this energy until 1935, when a new element was discovered. And this is the fission, the splitting of uranium-235 into krypton and barium Now, uranium-235 is a naturally occurring form of uranium, but it has the property that if you hit it with a neutron, then it immediately splits up into krypton and barium, and the mass of those decay products is less than the mass of the initial nucleus, so energy is released. But also, in this reaction, 3 neutrons are released, and those neutrons can go on to hit further uranium nuclei, which will in turn trigger those to split, releasing more energy and more neutrons, and you get a chain reaction. So this is the principle behind a nuclear bomb. But perhaps fortunately, this reactive isotope forms only 1% of naturally occurring uranium ore. So you have to find a way of enriching the uranium, of purifying it on an industrial scale. And that, at the start of the Second World War, is what this place was designed to do. In the early years of the war, this site was used to develop a technique to enrich uranium. But in 1943, much of the work here was transferred to America to become part of the Manhattan Project. Within 2 years, they had succeeded in building a bomb. On the 6th of August 1945, a uranium-powered bomb was dropped over the city of Hiroshima in Japan. As it detonated, the neutron-powered chain reaction converted 0.6 grams of matter into energy. The resulting blast flattened an entire city, killing over 100,000 people. It was as though science had finally delivered on those fears expressed by Mary Shelley over a century before. I mean, here, if ever there was one, is a Frankenstein's monster. Science had delivered the power to destroy us all, and there's every indication that the scientists working on the bomb at the time knew precisely what they'd done. After he witnessed the first nuclear bomb test, Robert Oppenheimer, the head of the Manhattan Project, felt moved to quote an ancient Indian text.
Now I am become death, the destroyer of worlds. I suppose we all thought that, one way or another.
It would be a couple of years afterwards I realised that I contributed to the atomic bomb. And I felt dreadful then when I thought about all the people that had been killed. But my brother, who was in the Royal Navy and was out in the Far East, said it killed a lot of people, but it would also save a lot of lives. If it helped to finish the war, which was a dreadful thing, yes, I feel pleased that I made a very minute contribution.
The development of the atomic bomb was a watershed moment in human history. For the first time, we demonstrated that the products of our own ingenuity could destroy us. And it had a chilling effect on the public's attitude to science. Where once the public were broadly accepting of technological progress, they were now suspicious and even hostile, some even taking to the streets to make themselves heard. It marked a change in attitude that's been felt ever since, not just by physicists, but by all scientists. If the first half of the 20th century was the age of physics and exploring the subatomic world, then the second half of the 20th century arguably was the age of biology, the exploration of the science of life. And that surely brought us closer to Davy's vision of the scientist as creator, as master of nature, rather than merely dispassionate explorer. And along with that came added dangers and controversy. These potato plants growing in a field in Norfolk are considered by some people to be dangerous. because they've been genetically modified. They were created here at the Sainsbury Laboratory, just outside Norwich, by plant geneticist Jonathan Jones. But he doesn't see these plants as monsters. Why would we, as a country, a civilization, want to use GM crops?
You can put in genes that you could not put in by breeding. And so there are certain genes that do something really useful, such as make it much easier to control disease, much easier to control pests, and much easier to control weeds. So there's a legion of things that are worth doing that you'd never be able to do by breeding.
These potatoes have been genetically modified to make them resistant to a disease called late blight. The hope is that yields will increase and the quantity of chemicals currently used to treat the disease will be dramatically reduced. It's remarkable that we have the ability to precisely manipulate and alter the genetic makeup of other living organisms. And that it's even possible is thanks to a revolution in biology that started in another part of East Anglia just 60 years ago. Cambridge is a town with a rich scientific history. This was the University of Newton and Darwin. And it was here, in a building in the 1950s, that the worlds of physics and biology came together to transform our understanding of life. This is the old Cavendish Laboratory, an iconic building in the history of physics. Thomson discovered the electron here in 1897, Chadwick discovered the neutron here in 1932, James Clerk Maxwell was Professor of Physics here. But the building is also famous for one of the great discoveries in the history of biology. In the 1950s, this office was occupied by Francis Crick and James Watson. So it might not look like much, but it was in here that the structure of the DNA molecule was discovered. That is the molecule that passes information on from generation to generation, the hereditary molecule, if you like. The DNA molecule itself had been isolated as far back as the 1860s. But it wasn't until the early 1950s that it was shown to be the carrier of genetic information in all living organisms. And although it was known to be made of a combination of sugars, phosphate groups and nitrogen-rich bases, nobody knew how those components fitted together to form a molecule that could hold the instructions for life. Crick and Watson's approach to finding that structure was to build physical models of the molecule. But it was proving unsuccessful. They desperately needed more and better data. And it came from a branch of physics called X-ray crystallography. This is a very famous photograph. It's called photograph 51. It was actually taken by another scientist, Rosalind Franklin, and it's what's called an X-ray diffraction photograph. So Franklin shone X-rays through a sample of DNA molecules, and the way that they scatter or diffract off the molecules, the pattern they leave on the photographic plate, allows you to deduce the structure of those molecules. The key piece of evidence is the X. That allowed Franklin to suggest that the molecule must be helical and, in fact, must have that famous double helix. So this photograph, along with Franklin's suggestions, interpretation of the pattern, allowed Watson and Crick to go away and build their model of DNA. This is a half-scale copy of the model they constructed in 1953, the first model of the structure of DNA. There are two strands of sugars that coil around each other. They interlock to form that famous double helix shape. They are the backbone of the molecule, but the information carried in DNA, the genetic code itself, is encoded into these pairs of molecules, the cross-link pairs, which are called bases. There are 4 types of base in DNA: adenine, thymine, guanine, and cytosine. And it's the order of these bases that's used by the cell as instructions to build strings of amino acids. The sequence of amino acids together build up proteins, and proteins build up the basic structure of every living thing on Earth.
We used to occasionally just sit and look at the molecule and think how beautiful it was. And I remember an occasion when Jim gave a talk to a little biophysics club we had. It's true they gave him 1 or 2 drinks before dinner. It was rather a short talk because all he could say at the end was, well, you see, it's so pretty. It's so pretty.
When Crick and Watson published their results in 1953, they announced them with typical scientific understatement. They said, this structure has novel features which are of considerable biological interest. But there's pretty good evidence that Crick and Watson knew exactly what they've done, because they ran down this street here from the Cavendish, just up there, into this pub here, the Eagle. And when they arrived, Crick walked in and said, we have discovered the secret of life. And then he had a pint. Crick was right. The discovery of the structure of DNA was one of the great moments in modern scientific history. By the early 1970s, the genetic code had been translated, making it possible to identify individual genes and study their function. We now had access to the workings of life itself.
What it did is it explained the physical basis of heredity.
At the time, Paul Nurse, a Nobel Prize-winning geneticist and now president of the Royal Society, was just starting his career. You began working in the field in, the 1970s, so this is only 20 years after the discovery. Was there disquiet amongst the public, but also amongst the scientists?
Well, there was, because, what these technologies were bringing along was that you could now begin to control this fundamental molecule of life. And people were worried about this. They were worried, well, if you can clone up pieces of DNA in a bacterium, let's say you had a cancer-forming gene, and that escaped, the bacteria escaped, would that mean everybody would catch cancer, just like an infectious disease? And frankly, these concerns are quite legitimate. Everybody was imagining Frankenstein-type outcomes.
In a post-nuclear age, there was a widespread feeling that scientists had once again taken a step too far.
Now, you made the statement there's no known dangerous organism has ever been produced by a recombinant DNA experiment. Now, just what the hell do you think you're going to do if you do produce one?
In 1975, biologists took an unprecedented step. Aware of the potential dangers, they called a conference in California to decide for themselves whether the technology was safe and how they should proceed.
What was interesting is that it was the scientists themselves who recognised this was an issue. It was the scientists themselves who actually put in place a level of restrictions depending upon the potential danger, so it could be kept under control. So it was very much led by the scientists as what should be done, rather than, say, the politicians or the public.
But although the scientists took the initiative at the beginning of the genetic revolution, they haven't always been able to control the debate. And nowhere is that clearer than in the controversy over GM crops in this country. To many scientists, GM crops hold the key to more efficient, more environmentally friendly agriculture. But they've been unable to persuade a sceptical public of the safety of the technique. Instead, public opinion has been led by a vigorous anti-GM campaign that started in the 1990s, and which has left many people dead set against GM crops. There are fears that the crops may contaminate the environment, or that they may be unsafe to eat. And underlying it all is a feeling that there's something fundamentally wrong about meddling with life at such a basic level. Yeah, what do you think of this label, Frankenfoods?
Yes, I don't know who came up with it. It's probably the Daily Mail in the mid-90s. The thing that's silly about it is that GM is just a method for conferring an improvement on crops. You know, the crops are basically the same, so to suggest there's anything fundamentally different about them is just stupid.
The suggestion is that because we can now put genes from an animal, let's say, a cow or a jellyfish or whatever it is, into a plant, there's something unnatural and therefore potentially dangerous about that procedure.
Well, the word unnatural is a real weasel word. I mean, it's unnatural to treat your kids with antibiotics. It's natural to let them die. I know which I prefer. Agriculture is fundamentally unnatural, whether it's organic agriculture or high-tech agriculture, conventional agriculture. We are eliminating all the trees and wildlife that used to be there and planting the plants that we want to have there to provide the stuff that we eat. So the thing we have to ask ourselves is, what's the least bad way of protecting our crops from disease and pests for reducing the losses caused by weeds?
As a scientist working on GM crops, you'd expect Jonathan to be a powerful advocate for the technology. But his view is also backed up by a vast body of research that shows it to be safe and effective. So if GM crops are to have a future in this country, the scientists need to find a better way to persuade the public to share their confidence. I think that sometimes many scientists, myself included, are genuinely baffled by the public reaction to a new scientific discovery or technique or piece of research. Because I want to believe deep down that if we present the evidence and explain it properly, then that's all you have to do. But of course, it would be naive to think that that's the case, and I think there are good reasons for that. One is that there is a genuine fear of the unknown, but also I think the idea that science is dangerous, Frankenstein, is deeply embedded in our culture. The way to combat that fear is through effective public engagement. And perhaps surprisingly, one of the best examples of that comes from over 200 years ago, and a scientist who at the time was perceived to be a dangerous villain. In the lobby of the Royal College of Surgeons stands a statue of John Hunter, a Scotsman and one of the fathers of modern medicine. In the 1780s, he started performing surgical operations that were decades ahead of their time. This is the original documentation of the case of John Burley. It's a really excellent example of Hunter's skill as a surgeon. There's a picture of a tumour, so that's what happens when you leave a tumour for too long. It says here, it was increased to the size of a common head, attended with no other inconvenience than its size and weight. And then the second drawing here is after the operation. It's completely cured, essentially. But for all his medical brilliance, Hunter was treated with suspicion and even horror, because to develop his remarkable surgical skills, he had practiced on human corpses. In the 18th century, anatomists were legally entitled to corpses fresh from the gallows, but even so, demand comfortably exceeded supply, and so they had to look to another source of bodies for experimentation. And the easiest place to get hold of fresh corpses was to dig them up from a graveyard. Grave robbing wasn't made a crime until 1832, partly because of the legal difficulty in defining what the crime is. So you can't steal a body because it doesn't belong to anyone. But even so, it was frowned upon, to say the least. So it was a high-risk profession. But anatomists were prepared to pay large amounts of money for corpses, and that meant that there were hundreds of grave robbers operating in gangs in London who could dig up to 10 bodies per night. They were even called the resurrectionists because they were so efficient at lifting dead bodies from the ground. And the best customer of all was John Hunter. Hunter was even known to lend a hand to the grave robbers. On one occasion, he was even arrested with a gang of resurrectionists. And these exploits made Hunter incredibly unpopular with the man on the street. Hunter revolutionised surgical techniques for the benefit of everybody, but I suppose not unsurprisingly, his work was controversial in public. So even though he was working in the 18th century, I suppose you could say, in the modern vernacular, he had a PR problem. Hunter was so afraid of the adverse public reaction to his work that he was actually in fear of his life. But he reasoned that fear was born of ignorance, and therefore education was the answer. And so he opened this museum to display his work to the public. His collection is still on display today in the Royal College of Surgeons. In these exhibits, people could see how Hunter was using corpses to learn about anatomy and physiology. You could even see his pioneering attempts at opening new fields of medicine.
What's that?
These chicken heads were the recipients of some of the first transplant operations. Human teeth? When's he done that for? Although some of these exhibits are gruesome, they show how Hunter was using his knowledge to move medicine out of the Dark Ages. This exhibit marks the beginning of the end of the age of barbaric surgery. What you see here is an aneurysm in the popliteal artery, so that's the artery that goes behind the knee. It's essentially a sac of blood. The artery swells up, and if this goes untreated, then what will happen is that sac will eventually burst and the patient will bleed to death. Now, the treatment at the time for that was amputation. They would saw your leg off. In an age before antibiotics, that was usually fatal in itself. So this was a very serious thing to happen. What Hunter noticed through his work on animal physiology and indeed on the dissection of human specimens was that there are many other arteries in the leg, and he reasoned that if he tied off the affected artery, ligated it, then the blood supply to the aneurysm would be cut off, and he hoped that the other arteries would expand to allow blood to flow down the leg. Now, this was the leg of a coachman who had that operation performed on him and survived for 50 years after the operation. He, in fact, outlived Hunter, and he was so pleased with that extension of his lifespan that he donated his leg to the Hunterian collection. As well as revolutionising medicine, John Hunter's approach was a model for public engagement. By inviting people into his museum, he was able to address and confront the moral objections to his work. And although not everyone was convinced it justified grave robbery, they could clearly see the benefits that his knowledge brought. The controversy surrounding John Hunter was different to many other scientific controversies because this wasn't a scientist exploring the unknown in a cavalier fashion. He had a specific goal in mind with which no one could disagree. He wanted to advance medical science. Rather, it was the morality of his methods that was called into question. And today, 200 years later, doctors can face similar dilemmas. One of the most emotive issues in science today is not the use of dead humans in medical research, but the use of living animals. To many people, experimenting on animals is morally unacceptable. It's a line we should not cross. Such is the strength of feeling that there are regular protests against the institutions and scientists who use animals in their research. This is not a modern phenomenon. In Britain, there's been a long history of animal rights activism. The first Royal Commission into the use of animals in research dates back to 1875. But in the eyes of many doctors, it's a necessary evil because of the medical advances animal testing brings. "13-year-old Sean Gardner had been paralysed for 7 years by a condition related to Parkinson's disease called dystonia. Until in 2006, he underwent a pioneering procedure. By passing current through electrodes implanted deep in Sean's brain, the surgeon Tipu Aziz was able to instantly relieve his symptoms.
He would be able to talk again. He would be able, hopefully, to participate in activities that are absolutely critical, like a normal education, and perhaps go out again and be a kid.
Within weeks, Sean was standing and walking again. It is in many ways a miraculous achievement. But this procedure remains controversial because Professor Aziz developed the technique by experimenting on macaques that had been deliberately given Parkinson's disease. How many primates were affected or were used in that research?
I would say across the groups, probably less than 100 monkeys were used. And to date, about 100,000 people have had deep brain stimulation for Parkinson's disease.
So I suppose a common public criticism of research in higher primates is that it's somehow a luxury. You know, it could be done in some other way. It may take a bit more time, maybe more expensive, but it could be done. So how would you respond to that?
Well, my response to that would be it could not be done because you can't replace an animal model with a cellular culture or computer modeling or imaging. And the advantage of using non-human primates is that, like us, they're bipedal. They're wired the same as us. And I never had any doubts about the benefits that accrued from the work that I was privileged to be involved in. Because this problem was so pressing, you see. These are patients who can't walk, fall over, drugs don't help them. And what you see is quite miraculous. These folks who are sitting in a chair, trembling, rigid, unable to move. And then you put electrodes into a target in the brain and see them suddenly getting up and walking like a normal person, regaining their dignity as a human being. It leaves you in no doubt about what you do, and I'm not embarrassed about what I do.
The animal testing issue reveals an uncomfortable truth about science. In order to generate the advances we want in areas like medicine, there are downsides and difficult decisions to be made. But it's my view that in Britain we get the balance broadly right, partly because of our long history of dissent and protest. The relationship between science and the public has always been a complex one. I think, in general, this great endeavour to understand the workings of the natural world is supported, and why not? I mean, I would argue that science is the foundation of our technological civilization. It's given us modern medicine, it's given us telecommunications, computing, air travel, the internal combustion engine, you name it. But even so, there seems to have been an underlying suspicion that there's something sinister there. Scientific progress is valuable, vital even. It might be that occasionally we reveal a monster. Understanding the atom did indeed give us the nuclear bomb. But that knowledge also opened up so many other opportunities. The thing about science, as with the acquisition of all knowledge, is that once it's out there, it can't be retracted, and you never know where it's going to lead. But having said that, even some of the most controversial discoveries have paid dividends in the end. In 1805, Giovanni Aldini was hounded from Britain for trying to resuscitate people using electricity. But now, we find machines that can do exactly that, all over the place. This is a defibrillator. You'll find them in many public places around the world, and it's probably the best chance you'd have of surviving a heart attack down here. It is essentially a battery connected to electrodes. The idea is that administering an electric shock can restart a stopped heart. So this is exactly what Aldini had in mind. It uses electricity to bring people back from the dead. Maybe he wasn't such a Frankenstein after all. Next time, I'll be coming face to face with the visionaries who laid the foundations of modern science. I'll be recreating some of their groundbreaking experiments and exploring their impact on the scientific discoveries of today.
Well, you can see that next Wednesday at 9. How vertebrae got their backbone and moved from the sea to the land and sky. David Attenborough's Rise of the Animals, Friday at 9 here on BBC Two. But next, entering the normally private world of portrait artist Jonathan Yeo. It's The Culture Show.